This video is part of the lecture for multivariable calculus, and I'm going to talk about derivatives of vector functions. So let's start. If I want to give you a recall, a vector function is a function like this, r of t. It's a vector with the components x of t. The second component is a function of t, we call it y of t, and if it is in a space, we have the third component z of t, and we can think of it as the position vector of a moving point on a curve in the plane R2 or in the space R3. If it has 3 coordinates, it would be in R3. Then we're gonna say that the vector function RT is continuous or differentiable, if and only if, so let me just move this one down, if and only if each component is continuous or differentiable. So when we want to check that a vector function is differentiable, all you need to do is to check each of the components that are differentiable or not. If you want to check that r of t is continuous, you just need to check if each of the components are differentiable or not, are continuous or not. And this notation is here is if and only if. What it means that if each of the component is differentiable, then the function is differentiable. If the function is differentiable, each of the component is differentiable. So it's like a definition of that. And then we're gonna define derivative of the function dr dt as this. We're gonna state that it's the limit. That's the definition of derivative, but for the vector function, r of t plus delta t minus r of t divided by delta t, as delta t goes to 0. If you remember calculus, we use this definition for saying that the function is the function is differentiable. So the function at t plus delta t minus the function at t over delta t. That's the definition. And as you see, this is a vector in here. R of t is also a vector, but delta t is a scalar that we multiplied by a vector. So the derivative of a vector function is actually a vector function. It's a vector. And then we say that if we write each of these vectors as the component and then subtract the components, we just have basically derivative of the first component, derivative of the second component, and then derivative of the third component. So we're gonna say that it's the function is differentiable component-wise. Since each of the components should be differentiable so that the function is differentiable. Let me give you one quick example. Just assume that the function rt is cosine t cubed plus 10t and e to the negative 5t. What is derivative of that? Derivative, as we said, it's a function it's a vector function, and then we just need to take derivative of each of the component. Derivative of cosine t is negative sine t. Derivative of t cubed plus 10t is 3t squared plus 10. And derivative of e to the negative 5t is negative 5e to the negative 5t. Okay? And since each of the component is differentiable, as you see here, the exponential is differentiable, polynomial is differentiable, and the trigonometric function is differentiable, then the whole RT is differentiable, and that's derivative of that. Now let's see, what do we have geometrically? Geometrically, just assume that we have x-axis, we have y-axis, and we have z-axis. And then we have this curve as or RT. So it's as we discussed in the previous video, a vector function, when we have just one parameter, it's gonna parameterize a curve. So we have just the curve in a space, and then I'm gonna just define what definition of the derivative is in the geometrically. So I'm gonna write r of t minus r of t plus delta t. I'm gonna see what it is. Okay, so just assume that at the time t we are here. So this is r of t, okay, from the origin. Let me give you one small note that every point we can represent any point in R cube by a vector. Starting at the origin. What it means that if we have any point, this is x-axis, this is y-axis, and then this is z-axis. If we have any point in this space, the point P, I can start the origin and then make a vector, and we call it the position vector. Call it the position vector, OP. So for any point, I can represent it by a vector where the vector starts at the origin. And so I'm gonna say that at the time t we are here, and as t passes at the time t plus delta t, I'm gonna be here and I'm gonna make it like this vector. And then RT minus RT plus delta t would be this vector. You see? So let's say that the moving point at the time t is in the point P. Let me call this point here the point P. The moving point at the time t plus delta t is in the point Q. Let me call this point here the point Q. And then I'm gonna say that the secant vector PQ would be RT minus R of t plus delta t. Okay, and then if you notice that as delta t goes to 0, then the vector r prime of t, where r prime of t is actually r of t minus r of t plus delta t over delta t, assume that delta t is positive, then as this vector goes to, as delta t goes to 0, then the vector r prime of t, it's gonna lie on the tangent line. How? It's like that. You see, if delta t is t plus delta t, I'm gonna be here, but the moving point, if delta t goes to 0, it means that if we have a smaller delta t, the point Q would be here, and the vector RT minus R t plus delta t would be here. And then if delta t is even smaller, Q would be here and the point would be here. And as you see, the PQ, this vector, it's gonna be lying on the tangent line as delta t goes to 0. So we're gonna say that r prime of t is the tangent vector. It's just because as delta t goes to 0, r prime, the vector pq, it's gonna be lying on the tangent line. Okay, and so since r prime of t would be on the tangent line, we're gonna call it the direction vector. It's direction vector of the tangent line. It's very important. It's just because we're gonna use r prime of t to find the tangent line. Okay, let's have one example. So as an example, find parametric equation of the tangent line to the curve x equals to t, y equals to e to the negative t, and z equals to t cubed at the point 0, 1, 0. So we have a curve like this, and this is the given curve. The first component t, the second component e to the negative t, and the third component t cubed. And at the point 0, 1, 0, we're gonna find equation of the tangent line. Okay, how do we do that? Well, we're gonna say that derivative of r of t is actually a vector that is tangent to the curve at a given point. So I'm gonna find r prime of t. Derivative of t is 1, derivative of e to the negative t is e to the negative t, and then derivative of t cubed would be 3 t squared. And I need to find parameter at this point. It means that at what time my point is here. How to do that? I'm gonna say that x is equal to t, y equals to e to the negative t, and the third component is t cubed at 0, 1, and then 0. What is the parameter? As you see, t is equal to 0, and let's check. If I plug in t equals to 0 here, I get e to the 0, which is 1, and then I have 0. So I'm gonna say that the parameter that I was looking for is t equals to 0. So at t equals to 0, the moving point is on that point. Okay, so Now I have everything that I want for writing the tangent line. For writing any line, actually, we just need a point, and the point is given. The point is 0, 1, 0, with parameter, the corresponding parameter t equals to 0. And I need a vector, a direction vector. The direction vector for the tangent line, it's gonna be the derivative. I forgot to put the prime in here. It's gonna be the derivative at the time t equals to 0. So it would be r prime at 0. It's just because, one more time, the derivative would be tangent to the plane, to the curve. And so I just need to plug in the parameter to find the actual vector at the time t equals to 0, which would be 1, negative e to the negative 0, which would be negative 1, and then 0. Now I'm gonna write the tangent line. So the tangent line would be x, y, and then z. I'm gonna put the starting point or any point on the line, which would be 0, 1, 0, plus the direction vector times t, which would be 1 times t minus 1 times t plus 0 times t. Therefore, the tangent line would be x equals to t, y equals to 1 minus t, and then z equals to 0. Okay, on the next video we're gonna talk about differentiation rules.